Okay, you probably saw the announcement that we're having the Shazam competition on Friday. There's an announcement on Piazza with the details of how to submit entry to the competition. So, hope that lab is fun. Okay, today we're going to talk about this notion of systems. If you look through course catalogs, electrical engineering required courses, you'll often find a course called Signals and Systems. And that's really this course, except for that we emphasize signals more, so we changed the title. But you'll see, hopefully you'll see how this ties in to the same topics we've been learning. I want to introduce the notion of a system that is acting on a signal. So we have some input signal, and we have some output signal. And what's happening is the output is a function of the input as a signal. So we might think of this as a time series, x of t, and we can label the output as y of t, and we often label the system something like h. And what I want you to think about here, in the context of why we would be discussing such a thing, is that this system might be, for example, here's a few examples, a signal processing algorithm. So maybe this system is doing something, smoothing or whatever else on an input and producing some output. Maybe it's denoising some audio recording or something like that. Okay, but there are many other things this system could be. It could be something like a circuit, and you might want to know, what is this circuit doing to a signal? Okay, it could be something like this could be a mechanical device even. In the first lecture, we said, the shocks of a car is a mechanical device, and we might want to know, what does that do? And a couple other examples. This could be a communication network. So the input there would be like the load and the traffic patterns through this communication network, who's trying to talk to who at what rates, as a time series. Things change over time. And you might want to know, can the system adjust to changing loads in a nice way? And that's what this analysis would be. It would be the output is when maybe things arrive, or what happens to the traffic within the network. And you could even broadly talk about something like a computer system. So really there's no limit of what this system could be. So here's an example. Maybe the input is what is typed on the computer, and the output is what is displayed on the screen. Okay, so there's a system with an input and an output. All right. Now, we have a notation for these systems, and that is that we usually say y is h of x. So it's just this function sort of notation, but of course y is a signal and x is a signal. These aren't just numbers. Now another way to write it, maybe more common, is to say y of t equals h of x of t. And just as we saw with convolution, this is sort of here, this is an abusive notation. But there's a reason for it. Just like in convolution, you might like this because it allows you to plug in something, instead of x that's like a time-shifted version of x or something, and it's very easy to write it, though it is less precise. So you just have to remember that notation really means the thing on the left. Same with convolution. Does anyone want to repeat to me what I said about convolution? Why this can be confusing? What is wrong with this? Yeah. Yes. Yes. So what you're saying is that this t should not be, I mean, if you want to be more precise, this t should come after the parentheses, because what's going on here is if you want to know y at a particular point in time, this notation incorrectly suggests that you only need to plug in x at that same time to some function. That's not what we're talking about, and we're not limiting systems in that way. The system can look at the whole input process to determine any one of the output, any time for the output. Okay, through some examples that'll become a little more clear. Okay, so what I'm going to do here is go through 6 system properties that'll be of interest. You should learn what these are, and then it's going to allow us to kind of narrow down what kind of systems are we going to want to analyze with the tools we have. Okay, so we'll get there. We'll list out these 6 properties, and then we'll kind of hone in on focusing our attention on systems that just have certain properties. Okay, so here we go. First property is memoryless. No. So some systems will have this property, and I'll give the definition for what it means, and then we'll try to identify through some examples, does this system have that property or not? Okay. So a memoryless system would be one. So we'd say H is memoryless if y of t depends only on current input, x of t, for all t. Okay. So more precisely, we can say that the requirement for memorylessness is that if x1 of t and x2 of t, 2 different signals, are equal at a given point in time, then their outputs that they would both cause are also equal. And this is for any specific t. Okay, so for all of these properties, I'm going to be using this x. I'm going to suppose that x produces y through the system, x1 produces y1, x2 produces y2. So let me go ahead and write that down. So for all these properties, okay, so for each, so let's just assume that y equals h of x, y1 is, y1, it's not one erase, okay, y1 equals h of x1, and y2 equals h of x2. So that'll just help me state the properties more easily. So here we're saying if the inputs are the same for 2 points in time, then the outputs they produce should be the same if it's a memoryless system. It doesn't matter what happens at other times. Okay. In fact, memoryless, the notation up here, the one I just complained about, that would be fine notation if we were only looking at memoryless systems, because that kind of implies that it's memoryless, although that's not what we want it to imply when we write it. Okay, let's now causal systems they're somewhat similar. They say that H, so it's causal if the output depends only on past inputs. Okay, so and this has to be true at any point in time. The output at any point in time has to just depend on what happened to the input up to this time. Okay, so it has this notion, this intuitive notion of causal, that things that happen in real time. So you can think of a causal system as sort of a real-time system. It means that you can't have the future inputs affecting the current output. You can't have things happening backwards in time. Okay. What? That's non-causal. Okay, good. I was wondering if you'd wonder, well, why don't we only look at causal systems? And really, the non-causal systems are just going to be systems that aren't running in real time. Think about like some MATLAB processing you're doing in the lab, where you have some time axis, but it doesn't really mean, I mean, it's okay for you to advance things in time and play it back because things aren't happening in real time. That sort of signal processing would be allowed in an offline thing. Okay, so there will be situations where non-causal systems are fine, and they all have to do with maybe the time axis isn't really time. Maybe it's space, like a photo or something. Or maybe this time is just a recording, and you can shift things forward and backwards. Okay, so a little note here. Oh, let's state this more precisely. So in each of these cases, I can give you a more precise mathematical definition. That's if two signals are equal for all time up to some t, then that means that the outputs need to be also equal up to that point. At that point, have to be equal. And this, again, would be true for any specific t if the system is causal. Okay, and a little note we can observe already that memoryless implies causal. So it's a stronger condition, right? If it's memoryless, then it's certainly causal. It's not depending on any other times, certainly not the future. And what we just discussed, that real-time systems are causal. Okay. Now, notion of time invariance. So time invariant here. Depending on the context, this is often referred to as shift invariant, and that name just means that the time axis doesn't always have to be time in your application. Talking about, and so let's look at what the definition is. So H is time invariant if the if you shift the input in time, the consequence is all you've done is shift the output. So I can write that as the following. That if I shift the input by t naught, for any t naught, or all right, then and I put it through my system, then the output is just what it would have been, but also delayed. Okay, so if your system doesn't have an internal clock, then it should be time invariant, right? If it's just sitting there waiting to respond to an input, and it doesn't matter how long it waits, it's going to respond the same way, no matter how long it's waited, then it's going to be time invariant. All right. So we could say if x2 is this is just rewriting the above, it's the time-shifted version of x1, then that would imply, for a time invariant system, that the output is similarly delayed in time or advanced if t naught was negative. Okay, so there's a time invariant system. Now a property we're familiar with here, linear. We already said what that is. So H is linear if H operating on, let's say, A x1 plus x2 is just going to equal A H of x1 plus H of x2 for for an arbitrary x1 and x2 and for all A. That could be complex numbers. Okay, so there we go. With that, we've already discussed linearity before. Let's last two properties, and then we'll dig in and look at some examples. Okay, invertible system. All right, and this means that you don't lose any information through the system. So if x, it's invertible if x can be recovered from y. Okay, so this would mean, as I said, no loss of information. And another way to say this is that there's an inverse system, H inverse, that exists where H inverse of H of x equals x, of course, for any signal x. All right, so that would be that we would call that invertible. And lastly, a system is stable if really what this is meaning is we want it to behave well for any bounded input. We don't want it to have very large outputs for bounded input. So we'd say H is stable if a bounded input always gives a bounded output. Okay, and in fact, there are potentially multiple ways of defining a stable system. This way is abbreviated BIBO because of this. Bounded input, bounded output. Okay, so we can state this one as if x is bounded, that means for all t, the absolute value is less than some value. I'll call it bx for all t, okay? For some bx. So if there is some number bx large enough such that x never gets bigger than that, then we would say it's bounded. And assuming that, and what we want in a stable system is that would imply that y of t is also going to be bounded by a different number, okay? But at least that there is some bound that holds for all t in the output. Okay? If that's going to be true in general, then it's a stable system. All right, so now we're ready to look at some examples and see if any of these properties made sense. Now, for these examples, I'm going to state the systems as a mathematical equation. In fact, that's, it's nice. The best systems are ones where we have a simple mathematical expression for what they do. Let's look at those examples. Of course, in reality, you might have some circuit, and you then need to, model it with a mathematical equation to tell whether it has these properties. Okay, so y of t. So here's 4 examples. All right. Okay, so we have 4 possible systems. I'll just label them. System 1, 2, 3, 4 that we're going to look at. And these expressions are telling you what this system is going to do to any input x. Okay, it's just going to calculate y according to this equation and output it. All right, so first of all, let's look at our first definition we came across, memoryless. In fact, I'll write all of the properties up here, and I'll fill in a table for what properties they have, and then I'll let you guys tell me which ones you want explained, and we'll work through some examples. Okay. Although it's always fun to make guesses, even if you're not sure. So as I fill in this table, I want to get some shout outs going on. Yes or no. So for memoryless, oops. Okay, so first thing is memoryless. Do we think that this first system is memoryless? What? You say yes. Do we have yeses? Okay, we've got some yeses. What about any no's? All right, so actually it is memoryless. I thought maybe the sign of t plus 1 would throw some people off, but it shouldn't. Okay, second one, memoryless or not? Yes or no? Let's say if yes, shout yes. All right, 3, memoryless? Any yeses? No, some no's. Okay, 4, is it memoryless? In fact, no. Okay, all right. So those are no's. Let's go on to causal. Now, causal immediately, if it's memoryless, it's automatically causal. So we get those for free. All right, let's look at those last two. Is the integral from 0 to t of a signal, is that going to be a causal relationship? Does y depend only on the past? The answer is yes. And then this last one, is it causal? And the answer is also yes. Okay. Let's go on to time invariant. Like I said, I'll come back to these, and we'll be able to go dig into any one of them. Okay, time invariant. System 1, is it time invariant? Remember what that means. If you shift the input in time, do you get the output shifted in time? And, in fact, the answer is no for system 1. System 2, do I have any yeses? Is this a time invariant? Turns out it's yes. Okay, system 3, any yeses for system 3? It's like an auction here. Okay, system 3 is also time invariant. And 4 is in fact not. That t messes it up. The t in front of the x of t. Okay, it's like a clock in the system that makes it change, the output depend on the current time. All right, linearity. That should be an easy one. Is that first system linear? I have a no. Okay, this actually should be tricky because the high school definition of linear is different than the definition I gave here. In high school, you think of a function like this. Forget about signals. Just think of this, ax plus b. That's your linear function, right? But that's truly not linear unless b equals 0. Okay, it should really be called affine. And linear must have the form y equals ax. The reason is because if you try that definition I gave for linearity here, it doesn't work. Plug in 0 in as x. So what we want to do is we'd want to try it twice with 2 different x's, right? And we could just use 0 both times for x, all right? And both y's would equal b. And then we'd say, well, what if we sum the 2 x's together first? Well, it's still 0. Plug it through here. I should get the same answer. But then you'd get a 2b in one case and a b in the other. If you added the 2 initial answers together, you get 2b. If you plug it in again, you just get 1b. So it doesn't work if your constant's non-zero. Okay, so that's confusing just because you were taught that this is a linear function when it's really an affine function. When we're talking about linear systems, you can't have a constant. So I'm going to erase this. But even though this definitely looks like a linear function because it's linear in x, yeah, but it's got this constant with respect to x that throws it off. So it's not a linear system. Okay. So the linear ones are these last 2, actually. The first 2 are not linear. And then for invertible, all right, invertible, remember, we want to know if you put an arbitrary x in and you get y, could you recover x? Okay. So which systems do we think are invertible here? 2? Okay, great. And 2 is almost invertible. I'm going to actually say no because you lose the sign. Yes. But it's very close to being invertible. Anything else? The first one is invertible, yes, because you could always just subtract the sign of t plus 1. There's one other one that's invertible. The integral, we know how to invert that, take a derivative. You would if you go the other way. So derivative loses the constant. Yeah. What about which ones of these are going to be stable? If they have a bounded input, you can guarantee they have a bounded output. The integral you say is, but it's not, because if you integrate a constant, it just keeps growing. Okay. There are two of these that are stable. The square, yep. And one more. Okay, the first one is stable, yep. The last two aren't. So let me just fill in the x's here. These were not. These were not. You like my examples? Every one of these has two except causal. Try to give you a little variety here. Okay, so let's go back and just actually dig in. I expect that for many of you, it wasn't clear why I answered yes or no on these. So don't be shy. Let's go back and see which ones we should take a look at. Maybe starting with memoryless. Is there one of these that wasn't clear why it was memoryless? Or why it wasn't memoryless? And you want to see how I would argue such a thing? I'll take one example for each. So let's just someone pick one here. The last one, yeah. Okay, so we're saying, so let's work out why. So 4 is not memoryless. And so I'll first start by just saying in words why. And it's not because, I would say, looking at that formula, y at time t doesn't just depend on x at time t. It also depends on x at another time. In this case, t minus 1, not the current time. So in words, that's why I can identify that this is not memoryless. However, an argument using the mathematics would be to say, okay, let's just give an example of an x. All right? How about this? How about x1 of t equals, let's say, rect of t, and x2 of t equals rect of t over 2. Okay, if you want to visualize what these are, rect goes like this. It's 1 between negative half and half, right? And rect of t over 2 stretches that by 2. So it's 1 from negative 1 to 1. Okay? And now what I want to say is, remember the definition said if two things are equal at a point in time, their outputs they produce should be equal. So I'm going to look at time. T equals, I can pick any point in time I want. So time t equals a half. Let's let t equal half. Okay? Now, notice that, or maybe I should do a quarter just so that there's no confusion on whether I'm on the edge or not. Let's say t equals 1/4. So t equals 1/4 is like this, right? They both have value 1. So for a memoryless system, the output at t equals 1/4 should be the same for both of these inputs. Okay, because that's what it means to be memoryless. The output only depends on what's happening right now at the input. But we can calculate the outputs here. We'd get y1 at 1/4 equals, plug in here, 1/4 times x1 at 1/4 plus x1 at, instead of 1/4, it's minus 3/4, right? Okay. y2, similarly, equals 1/4 x1 of x2 of 1/4 plus x2 of negative 3/4, and here's where we're going to see that they're actually different, because this x1 of 1/4 is 1. Both of these are 1, so I'll write it like this. So these are 1, right? But these here that's 0, and that's 1. So you're going to get different answers. Okay, is that clear? So So it's easier, except it's harder to write it out live here, but it's easier to just work out what is y1 as an entire signal. Okay? You could work it out. You could go calculate for all values of t. And what is y2? And then we could easily identify, oh, these differ at points even where their inputs were the same. Okay, so it has memory. It depends on more than just the current input. Okay, great. Let's look at another example. Maybe go to causal. You want me to argue why things are causal? You know what? I'm not going to have we could work out an example just like this, but it's going to be very pedantic because I can just argue in words and convince you, I think, that these two that were not memoryless. Remember, the memoryless ones have to be causal. The two that are not memoryless, if we want to say, why are they causal? Let's look at the same system, 4. And realize that to calculate the output at any time t, you do not need to know future inputs. A future input would be x at some t plus some positive number. Okay, and that doesn't exist in the function. So we just know from inspection that this will not depend on the future, therefore it's causal. Okay? Yes? Yeah, that's good. Because it's not depending on the input signal. X is the input, and think of sine of t plus 1 as just some function. It's like hardwired into the system. And it doesn't depend on the input, so it's okay that it's a sine of t plus 1. That's not really looking at the future because it's just some known signal. But that's, yeah. So, I did that on purpose to draw out that question, right? Because if it were x of time t plus 1, it would not be causal. But sine of t plus 1, you can calculate that without knowing the input for any t. Right? Okay. Good. How about time invariant? Do we have one we'd like argued for time invariant? Which one? All right. Someone better raise their hand because we got it. We still have more stuff to do. They're all crystal clear? I don't believe that. Which one should I do for time invariant? The first one. Okay. So the first one we're saying is not time invariant. To prove that it's not a certain property is easier because you just need an example like I did for system 4. Because all of these properties say something about something should happen for all t, right? Basically all these properties have that in there somewhere. For all time, you need something to happen. So showing that doesn't happen can work by example, like this case. So I know by looking at this that it's not time invariant because I know this. If you shift the input by delaying or advancing it, the sine function doesn't shift, right? It's not depending on the input. And so that's where this thing's not going to be time invariant. Think of this sine of t plus 1 is you have some clock in your system that's calculating sine of t plus 1, and that affects your output. Of course, this clock, an internal clock is not going to be time invariant. So to prove this, I'm just going to do an example. I'll say, so we want to, again, 1 is not time invariant. And all I'm going to do is take an x that's, this is easy. I just need to take x equals 0 to do my example, right? Because let's let x1 of t equals 0. Let's let x2 of t be a delay of that. X2 of t equals x1 of t delayed by, with a time delay of 1. That'll work, okay? So, of course, that's still 0. But it's important that I say it's x1 with a time delay. Okay, so this example is going to seem too silly, but you'll see what happens. What's y1 of t? According to this system definition, what is y1 of t? You can't see it, but maybe you remember. Plug in x1 of t here, which is 0. This is just sine of t plus 1. Okay, what's y2 of t? What is it? It's also sine of t plus 1 because, remember, I'm just plugging in x2 equals 0 into that equation. Okay? So, obviously, y2 of t does not equal y1 of t minus 1. Because that would be sine of t. They're not equal, right? Okay, so that example, you might say, well, gosh, can I really use such a simple example? It's like cheating. Does it give any intuition? Well, really it does. I'm just really highlighting what the part of the system that's not time invariant. It's this thing that's not depending on the input that has a t in it. That's messing it up. Okay. All right. How about linear? Let's see if we can move quickly, because I want you to see examples of everything, but I might, you know what, I'm just going to go through and say in words some of these, and you can ask the TAs questions. We'll have, next week we'll have review sessions because we have a midterm coming up. All right? So please, ask questions, especially these ones we didn't get to do here. Make sure you understand how to know whether linearity holds or not. But in words, I mean, linearity here, we already said the first one is affine. So if you can come up with examples, again, just use x equals 0. You're going to see that it's not linear. Okay, square, that should give it away. That's not going to be linear. This is linear because we know that differentiation and integration are linear, that if you add things together, you can separate the integral. And similarly here, you can just try it out. But it's linear because this t, you might say, what, this t x of t doesn't look linear. But remember, we're talking linear with respect to the input signal. T is just some constant compared to the input signal. So if you try out the rule for linearity, it's going to still work here. Okay. Invertible, yeah, we know we can. There's just a couple notes for invertible. It was pointed out that 2 is almost invertible. We're just missing the sign. Sometimes you get these things that are almost invertible, and you might be willing to just kind of think of them as invertible. We lose whether it was positive or negative at each point in t. All right. And this last one is almost invertible, except if you knew x for any interval of length 1, then you knew y, then you could calculate x for all the rest of time. But there's a little bit of ambiguity in x. You can try it out. You can't actually recover x fully just from knowing this. Okay. Great. So now what we need to do is focus in on these properties we're going to really care about. We sort of care about all of them in different settings, but we're mostly going to focus in on systems that have these two properties, linear, time invariant. In fact, this is such an important part of this topic material that people just refer to these as LTI systems, and you'll hear that a lot. An LTI system. And that's really what the tools of this course can address very well. Okay? Now, why would that be enough? Why should we focus in on that? Well, for one thing, these do occur frequently in nature. Let me just argue that real quick. Okay, so physical laws are, for the most part, time invariant. I mean, well, they are. So if you start some physical experiment at a different point in time, assuming everything in your universe is the same, then you would have then the laws would still behave the same. So physical systems are often going to be time invariant, and they're often linear. Can we see some examples of linear systems? Well, waves, sound, light. There are many examples where you get linear properties. Okay, so if we wanted to analyze some physical system, there's a good chance linear time invariant will be meaningful. Now, when not linear, because you do have nonlinear systems, it can be useful to linearize. So you make a linear approximation. They call this linearizing, and it's actually the way you would do it, you already know. You would just use the Taylor expansion, just use the Taylor approximation of first order. So even if you have some nonlinear system which behaves, maybe in some complicated way, a common technique in design and analysis is to say, well, let me linearize around some point I care about. Why? Well, it's because we're going to have so many cool tools for LTI systems. And you're just begging for your system to be LTI, and that's the reason to do that. Okay. Now, one other thing. And you have shift invariance in other areas too, which I won't get into, like optics. You have shift invariance, not time invariance, but shift over your lenses and stuff. And so you also come across shift invariance in things in the convolutional neural network. If you're in machine learning, you might recognize that name. It's a technique where you impose a shift invariance, so and other things. Okay. And finally, another reason to focus on LTI systems is that LTI signal processing. So forget about a physical system you want to analyze. Suppose you come up with a signal processing algorithm. Well, doing linear time invariant signal processing is very popular. So I hope I've given you some reasons to care about LTI systems. Now let's go see why focusing in on linear time invariant systems is going to be very helpful to us. Okay, first of all, we have this notion of an impulse response. So in continuous time, we would say the impulse response of a system, h of t, let that be the output that the system produces when you put a delta function into the system. Okay, now this is that delta function we defined previous lecture, right? The Dirac delta function, because this is continuous time. In discrete time, same thing. Of course, the delta function here is much simpler. It's the Kronecker delta function. It's a very simple function to understand. Okay, so suppose you put that signal into your system and you get something out. We'll call that the impulse response. Now, the cool thing is this. H of t, this isn't the cool thing. This is just restating what it is. All right. So think of a delta function as a tap, right? If this was some physical system, what would a delta function be? It would be some tap times 0. Okay. So you say, what does the system do if I tap it? All right. Now, here's the neat thing. If H is LTI, then the impulse response is a fingerprint. Of the system. So what that means is the impulse response tells you, identifies the entire system. If you know the impulse response, you know everything it's going to do. It seems weird because in general, to know everything a system's going to do, well, you better have some systematic way of trying every input. Okay? But for a linear time invariant system, if you know what it does in response to a tap at time 0, then you know what it'll do to any input. All right? So that's the cool thing, and I'm going to show you why in a moment. So, but for intuition, I'll first let you notice that you might identify this property yourself here by just trying an example. Suppose you have a discrete time system, like a signal like this, 0, 1, 2. Okay. So suppose you're interested in figuring out what is a system going to do that's to an input that's 1 at time 0, 2 at time 2, and 0 every other time. Okay, so this input signal is very simple. All right, and now suppose I know the impulse response. So this is x of n, and I have h of n here. Remember, h of n was what comes out if you just put a delta function in. By the way, a delta function is like just this part of our signal. Okay, so we know that what would happen in that case would be you'd get 1, 2, 2, 1. Okay, that's part of my example yet. I haven't worked anything out. And I say, now can you figure out for me what's going to happen what's going to be the output of this system when x goes in instead of a delta function? This was what happened when you just put a delta function in. So now I want to know what happens when I put x in. Well, the thing is that I know that this system is both linear and time invariant, and I can use that to my advantage. I can say, well, I know that this signal is a sum of two different signals, one that has a delta function at time 0, and another signal that's a delta function at time 2, but scaled by the constant 2. So I can decompose this into the sum of two simple signals. The first one I already know the answer to, right? I already know that first signal, that the output in response to that first input at time 0 is going to be the impulse response. Okay? So that's from x at time 0. But I also now can say, can I figure out what's going to be the output in response to this second non-zero input? Okay? Well, I can, because I know it's time invariant. So I know whatever it did to the delta function at time 0, when I put a delta function at time 2, it does the same thing delayed by 2. And by linearity, I know that scaling by 2 is just going to scale that output. So in other words, I'm going to have something like this. That, in response to the second input. And then I would need to add them up by linearity. All right? So this is from x at time 2. I get the green, right? Okay. And then lastly, I would sum them to get the entire output. So you see that I sort of, just from knowing the impulse response, I sort of have a way to figure out what happens to every input. Let's look at this generally, and we would say that first of all, we can always represent any input signal as a sequence of delta functions, just as I did above. Okay, so then what I have is this following argument. The output is going to be it's h of the input by definition. But here's the step where I'm going to represent x as a sum of delta functions, each scaled by the value of the signal. It's a delta with a delay. Okay, we've talked about this type of representation before. We're just representing x as simple delta functions, but you also can just see that this is exactly the sifting property. Okay, we've written that down as what delta functions do, which means this even works in continuous time. So for the intuition, we'll talk about discrete time. It's easy to think of x of n as being a sum of delta functions, but this same argument holds for continuous time, that sum is an integral. And essentially, we're saying even a continuous time signal can be thought of as a bunch of delta functions in sequence, except that it's not just a sum of delta functions, it's an integral. Okay. And nextly, we're going to say, by linearity, we can pull that sum out and say we can pull the sum and the constant x of k out, because these are each signals in terms of n. So this is going to be h operating on delta of n minus k. So how did I know what to pull out, what not to pull out? Well, first of all, I can pull out linear things like sums, but also parts that don't depend on n, because this is a signal where n is the independent variable. And so the system has to operate on those signals. But these are constants with respect, it's just a sum of a bunch of k's. All right. And that equals a sum over k, x of k. And now we know what happens by shift invariance. This is the impulse response shifted by k. All right. And do we recognize what this is? It's convolution. I heard someone whisper that. X of n convolved with h of n. So there's the punchline of today's lecture. That for LTI systems, let me give the arguments here. That was because of linearity. That was because of time invariance. So we used those properties, and we said that And now we see that any linear time invariant system is doing only one possible thing. It has an impulse response h, that can be anything. But given the impulse response, all it's doing is convolution of the input with that impulse response. So hopefully we're tying together the convolution idea to this lecture. So for the final statement I want to make here is that LTI equals convolution in some sense. So that's the idea today. That is that that statement can be understood in two parts. Convolution is linear and time invariant. Okay? And two, so we already saw that it was linear. We did that as one of the properties of convolution. Now we see it's also time invariant. Two, any LTI system does convolution. So these are really equivalent. Now you know one of the main reasons why we care about convolution. It's because the same reasons we would care about LTI systems are the reasons we care about convolution. And lastly, to understand an LTI system, we only need the impulse response, how it responds to an impulse. So it's not true for other systems, but it is true for LTI systems, that you just need to know the unit impulse response, and then you know everything the system will do.